Alright, this is my first attempt at the backwards classroom. We're learning about section 7.1, ionic bonding. Let's get started. What's shown here is fool's gold, and it's an ionic compound, a typical ionic compound. It has a little bit of that color of gold, and people have been fooled over the years to dig for it and have spent their lives digging for it. And ionic bonds are very strong, and what we're going to do here is learn about how ions are formed. So what we're going to learn in this section is how are ions formed and how do they form compounds. Okay, in this we're going to form sodium chloride. But before you can form sodium chloride, which is edible, let's look at what sodium is. Sodium is a metal. Metals can conduct electricity, so sodium can conduct electricity. It's silver colored, it's soft, it's malleable. That means it can change its shape. It'll explode in water, and when you put it in water, it makes a base, lye, and bases turn fat into soap. We played with sodium earlier. I took a piece like this out in the classroom, and I used my tongs, and I was able to cut a piece of it off of the sodium.
Oh, I see, because it's sodium.
While salt is a yummy food, chlorine doesn't look like it's part of salt. It's a green poisonous gas. It's in pools. It turns out that when you form a compound from its elements, the properties of the compound are not necessarily at all related to the properties of the elements from which it's formed. Just because sodium and chlorine have certain characteristics doesn't mean that sodium and chloride will have a mixed set of characteristics. That's for mixtures. Compounds have a totally new set of characteristics. Chlorine gas has a faint green color. Sodium chloride is a nice white crystalline solid that we put on our French fries. This is natural sodium chloride that's often found in dried lakes that have a high salt content. So compounds have properties that are not related from the elements from which they form. I would write that down. While sodium is a metal and soft, and chlorine is a gas and green, sodium chloride is completely different. It's got a high melting point. It's food. It's stable. It conducts electricity when it's melted only. Its crystals are cube-shaped, and it's brittle. Those properties are completely different from the elements from which it's formed. Okay, the first thing we need to learn about is valence electrons. Understanding what a valence electron is very important. So, I added the definition. Electrons in the outermost occupied energy level. It's written right there. Make sure you know it. If you'd like, take a moment and write down these notes. Now, how do you find the number of valence electrons? So easy. You have to look at the rings, and you have to look at the outermost ring. Sodium is 2, 8, and 1 in its first 3 rings. So 1 is its outermost ring, so it has 1 valence electron. Chlorine is 2, 8, and 7, so it has 7 valence electrons. You should be able to find the number of valence electrons of any atom on the periodic table pretty easily. Every now and then there'll be an exception, but you should be able to do it. Valence electrons are the electrons on the outside, and they really do control the behavior of the atom, and they also affect the way the other atoms interact with it. When I first started teaching, I encountered my first crazy spiky-haired student with this weird thing around their neck with spikes. Why would anybody want to wear a weird thing around your neck with spikes, or a weird thing around your wrist with spikes? And I would just want to stay away from them. And you can't help but judge the atoms based on how they look on the outside, and they do operate in that way, and that's why the valence electrons are most important. it's really not fair to judge people by the way they look on the outside. But take a look at this dude here. He's got the thing sticking out of his nose, the weird twos on his face. What the heck? There's got to be something wrong with this person, right? What if you knew that he donated over $6 million to some charity? Well, A, you'd be surprised, but B, you just can't tell. But you can't help. What would you do if you walked to someone who looked like that? You'd be forced to judge them by how they look on the outside. And that's how it is with the atoms too. And the valence electrons are the things that are on the outside. Now, there's a real easy way to tell how many valence electrons by looking at the periodic table. Maybe take out your periodic table so that you could be looking at it while I describe this process. If you have to stop here, do so, and find yourself a periodic table, even if you have to flip or use the internet or whatever. But the first column, hydrogen, has 1 dot, 1 valence electron. The second column usually says 2 on the periodic table, where beryllium and magnesium are, has 2 valence electrons. Let's not really focus on the middle so much. The middle part are not representative elements. The first 2 and the last 6 columns are called the representative elements. Boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon 8. The ones below all of those elements have the same number of valence electrons as the one above. So if boron has 3 valence electrons, so does aluminum, so does gallium, so does indium. If carbon has 4, so does silicon, etc. So from this pattern, you can tell the number of valence electrons of all the elements. The ones in the middle or the bottom, it does vary a little bit, but you can predict that it has 2 unless there's a good reason to think otherwise. All right, let's look at the pattern again. Hydrogen, 1 valence electron, skip the middle, 2. Now sometimes we call boron group 13, sometimes it's called group 3. The 13 is the new way, calling it group 3A is the old way. But at any rate, if you just look at the ones place, it has 3, 4, 5, 6, 7, 8 valence electrons respectively going across. This pattern you will have to memorize. So take some time and look at this pattern that you see here and make sure that you memorize it. Also understand that the first 2 groups, the lithium and beryllium group, are the S part of the periodic table, and boron, carbon, nitrogen, and that whole block over there is the P part of the periodic table. And just to reiterate some ideas from the previous chapter, the transition metals are the D part of the periodic table, and the bottom part is the F part of the periodic table. All right, this is another important slide, the octet rule. Must learn it. Atoms gain, lose, or share electrons to have 8. So the question here, which elements tend to gain electrons, which atoms tend to lose, this is also important. Geez, this is an important PowerPoint here. This is an important podcast. The metals tend to lose, they're on the left. The non-metals tend to gain, they're on the right. They lose to either fill up or empty their valence electrons. The noble gases, the elements on the extreme right, helium, neon, argon, krypton, and xenon, they are stable, they are unreactive, and they don't gain, they don't lose, they don't share, they don't do anything. Whoa! Who are these people? These are my favorites when I were growing up. These were the people that people aspired to be. That's Farrah Fawcett on the left. That's MJ on the right. On the bottom, that's Lee Majors, the $6 Million Man. That's a sound effect for the $6 Million Man. This is who people aspire to be. The elements aspire to be like the noble gases. The high school students, who do they aspire to be now? If you look in the halls and look at some wannabe student, who are they looking to try and be like? That's 45 Cent and Brittany and Bianca. These are the people who people aspire to be now. There are some students, who want to be 50 Cent. They need to hit the weight room before they accomplish that. Others might have to, go for a run and maybe, like me, lay off the jelly donuts for a little while, gain and lose, buy something, take something off to look like you're the icon. So it is with the atoms. They have to gain or lose to obtain an octet, and that's the essence of the octet rule. I admire Barack Obama, and if people would aspire to be like him, I think that would be okay. I heard that LeBron is getting engaged. Who's that on the left? I don't even know who these people are. So since the noble gases already have the number of valence electrons that they desire, 8, they don't gain or lose or interact with other atoms. Neon and argon are unreactive. And in 1916, Gilbert Lewis invented the octet rule. In forming compounds, atoms tend to achieve the electron configuration of a noble gas. Now, on the top here, the goal of elements, it seems, is to look like noble gases. So chlorine, up here on the top, has 2 in the first ring, 8 in the second ring, and 7 in the third. But if it would go chlorine 288, then it would look like argon. That's what chlorine wants to do. It wants to change its electron configuration to look like argon. On the bottom here, sodium is 2, 8, and 1. What noble gas is 2 and 8? That's neon. So if sodium would lose the 1 electron, then it would look like neon, and it would be more stable. So sodium and chlorine become good trading partners because chlorine wants to gain 1 and sodium wants to lose 1. But when sodium loses 1, it becomes positive. When chlorine gains 1, it becomes negative, and then they're attracted to one another. I think here's a good point to stop. I'll probably add and post more of this podcast tomorrow, or maybe I'll have it done now, but this is the stopping point. I don't expect you to get past formation of cations. Let's stop right where we are. Maybe if you're done with your gizmo tomorrow, you'll be able to use the computer to watch this part of the podcast with your headphones. And we'll learn that cations are positively charged ions, and we'll figure out how they're formed. Let's move ahead and start doing that if you're going to continue, or you can consider your homework complete. Go back and check whatever you need to make sure you understand.